before you can actually feed it to a model for training, and why this is actually critical for resource efficiency in ML. Okay, so just kind of to get a broad picture, I think it's a really exciting time to be building systems for machine learning, because there's a lot of growth in a lot of dimensions. So ML is being applied in more and more use cases. The model sizes are increasing over time, and the amount of data that we train on has also been increasing over time. And thankfully, this has been coupled and actually enabled by an increasing amount of computation enabled by machine learning hardware accelerators. So here's an example of the Google TPU pod, for example, that's powering doing a lot of these training computations. But unfortunately, this has also led to a large growth in cost. Okay, so training these machine learning models requires many GPU TPU hours, which translates into high cost. And so this is actually a slide from a colleague of mine, Zurich, at ETH. This is a project they did where they trained a 100 trillion parameter model for 1 day in Google Cloud. And I'm wondering what you think this cost. As a hint, they used 3,000 CPU cores, 64 A100 GPUs, and 360 terabytes of RAM for 1 day. So who thinks this was 4,000? 40,000? Okay. 400,000. Yeah, you're getting the point that it's expensive. In this case, it was still an academic project. It was 40,000. But still, this is, being able to burn kind of the equivalent of what can buy you this sort of car within a day on the cloud. And yes, there are models. Another example is Mosaic ML is a startup that has recently celebrated training a GPT-3 quality model in just under $500,000. Which is exciting, but if you step back, this is still $500,000, and clearly this is not sustainable. So addressing kind of this cost and resource efficiency problem for machine learning is a real thing. So that brings us to this high-level question of what can we actually do to reduce the cost of ML? And I think that's a really important question, because clearly we need it. The current kind of scaling of things is not sustainable. But also, it's really interesting that you can approach this question from many diverse angles. And I won't have time to cover all of these in today's talk, but I think I'll just kind of highlight them at a high level before diving into the resource efficiency question, which will be the one that we focus on. And I think what's interesting here is that addressing this question really has a lot of opportunities of looking at this intersection of systems and ML. So one way you can reduce the cost of machine learning is to maximize how well you utilize whatever hardware you are using. Okay, and we'll talk about that. Another thing you can do is try to use cheaper resources, right? So for example, we had a session on ML training on transient resources. So making somehow the hardware you use cheaper, but still making it useful for whatever you need to do. Another thing you can look at is making aspects of the model training inherently more efficient, for example, by sparsely activating models or having sparse model architectures. And so when a training example comes in, it doesn't need to activate the entire network, but can serve some kind of more, just a part of a network, be routed through a part of the network. This is kind of also inspired by some of this projects from Google, for example. The Pathways project has some of these goals. And then another way you can be efficient is which data you train on. The amount of cost and time you spend training is proportional to the examples you actually visit and see. And so training on the most important or relevant data is another way that you can help reduce cost of the ML. And I think it's really kind of requires taking a multi-dimensional approach to truly address this big question of how to reduce the cost of ML. But sort of for the purposes of this talk, I'm going to be focusing on this resource efficiency aspect. And what we basically want to do is ensure that a job makes good use, and we'll talk about what that means, good use of its hardware for machine learning so that this job finishes faster, and we therefore pay for those resources for less amount of time. Right? That's taking the perspective of a user, for example, renting resources from a cloud. But also, if you are the cloud provider, you are also incentivized to finish jobs as fast as possible so that you can then pack new jobs to that same hardware that you operate. And so which hardware do we care most about? it's really the machine learning accelerators like the GPUs and TPUs that are the most expensive components. And so these are the ones that we want to make sure we make high use of. So why on earth might we not have high GPU or TPU utilization? What can actually hinder that? And so it turns out that because, as Marco also showed, the performance of GPUs has been increasing with each generation. The amount of flops they can provide is increasing. But if you're not careful, feeding data to actually, for these GPUs that are training these models to ingest at the rate that they can really do these computations can easily become a bottleneck. Right, so if we picture this, we have the hardware accelerator where the training is happening, but this training needs to happen on some batches of data. And there's kind of this extract, transform, and load pipeline where you need to read data from storage. It's large volumes of data you're training on, so probably that storage is remote. Then you need to usually do some kind of operations on this data before it's really ready to be put onto the GPU. And I'll tell you more about examples of those kind of operations. And especially because these tend to be generic user-defined operations, they often run on CPUs. And therefore, this can become a bottleneck. So yeah, and feel free to interrupt with questions also, but I'll dive in a little bit deeper to tell you about what I mean by sort of these input data processing operations. So you have raw data on one hand. This is the data you actually collect. On the other side, I put training and serving. In this particular talk, I'm mostly going to be focusing on training since this is the more resource-intensive side of things. But basically, what you do with your raw data is you need to do some kind of cleaning of that data, extracting features. You might be normalizing the data. There's some kind of pre-processing operations you run. And some of this pre-processing you can do offline. And you can maybe just do once, collect that data, clean it, then store the materialized output of that pre-processing step into storage. And for this, common frameworks would be Apache Spark, Flume, etc. The kind of pre-processing that I'm actually going to be focusing on in this talk is what happens online. This means actually while the job is training. Like you're reading data, you apply some transformations on the fly, and then you load these onto the accelerator for training. And so and the reason we focus on this, sometimes called the last mile data processing pipeline, the reason why this is important is because this is the part that can potentially actually stall your training job, can stall how fast you put things onto your accelerator. And you might wonder, why do you want to do operations on the fly? Why not do them all in this pre-processing offline step? There are certain things that you want to usually tune. For example, you want to tune the batch size depending on the GPU you're using. You might also want to introduce randomness to your data. So maybe you read your input data set multiple times. For example, you're doing training on ImageNet. You have this image of a cat as one example. But every time you iterate each epoch, you want to augment that data perhaps in a different way. And that can actually help train your model to recognize this is a cat, regardless if it's top left or bottom right of the image. And so these kind of things can actually help you get better accuracy or more robust models. And so instead of storing all the random permutations of these images, you might just want to have one copy that you then randomly permute differently every time. And so for things like this, where you want to enable experimentation, like filtering different features, sampling different elements, applying different random permutations, or just adjusting to whatever the training job's parameters are, like what kind of batch size for this GPU, these are examples of operations that fit in this kind of online while the job is training mode. And as we said, this is the parts of the input data processing that can directly impact the training time and therefore the cost of these jobs, because you allocate all of these resources drawn on here for the whole duration of the training job. And this is particularly kind of a problem that's becoming more and more pressing because, as we said, the performance of the ML hardware accelerators continues to increase, but the host CPU performance is tanking or plateauing, and so we have this increasing disconnect. Now, the other reason to care about this input data processing pipeline is not just because it can become a bottleneck in your training job, but also because it actually consumes a significant amount of CPU cycles and energy. And so kind of quoting this, something that Marco also alluded to, there was a study from Meta or Facebook that looked at data preprocessing. They found for some of their models, it takes more power for the preprocessing than for the actual training. And we also did a study at Google where we looked at millions of training jobs. So I think Facebook's study was mostly on recommender system models. And this was very illuminating to see how much data processing contributes for their workloads. And then the Google study looks at kind of a more broad set of models. And its findings are that basically around 30% of compute time is spent in the data processing stage versus the actual training job. So the way we do this, you can think of kind of just like on a cloud provider, you might have like Amazon Elastic Units or some sort of normalized measure of compute power for whatever platform you're executing on. And so, for example, there's some amount of compute power for, or compute cost for CPU time and GPU time or TPU time. And you can sort of think of your compute units spread across these in some normalized currency, and 30% of that would be spent on the CPU side doing data processing. On average for the jobs that we did study in this, it was like a 1-month study over, I think, around 2 million jobs. So there's a significant portion of compute going into data processing, and it's worth actually thinking about how can we make it more efficient? Not just how can we make it faster, because that's also important, but how can we actually spend less energy on that time? So that's going to be kind of the outline for this talk, is how can we optimize this ML input data processing part of the pipeline. So I'll talk about 3 different approaches. I'm going to focus mostly on the second 2, but I'll talk a bit about each. So the first approach on this list is auto-tuning. So this is the idea that we're given some amount of resources on a training host, some kind of CPU cores, memory, and the question is, we have this input data pipeline that we need to run. How do we allocate to each operator in this pipeline the right amount of CPU time and memory so that we can operate that pipeline at the highest possible throughput given those resources? The next topic will be disaggregation, which is realizing that at a certain point, whatever ratio we pick, however much CPU cores and memory we decide to have in the hardware attached with a certain amount of GPUs, getting that ratio exactly right is going to be hard because each job has different requirements, as we'll see. And what we really would like is more flexibility to scale the resources we need for data processing separately from those for training. So we'll talk about how we can actually decouple these things and scale out data processing to multiple nodes. And then finally, I'll talk about how we can then, after having decoupled data processing and training, how we can leverage this multi-job view of data processing to do that processing in a more efficient manner. So in particular, things like caching and auto-scaling. So I'll start with auto-tuning. And actually, before diving into auto-tuning algorithm or anything like that, I'll just kind of set the stage for an example framework that I'll be using throughout the talk. There are multiple frameworks you might use. So I mentioned early on, if you were doing this offline data processing, you might use something like Spark or Beam, Flume. For the online data processing, it's typically a framework that's directly integrated with the ML training framework. Like in the case of TensorFlow, tf.data is the native data loading framework. In PyTorch, there's PyTorch data loaders. NVIDIA also has a library called DALI, which they use to offload some data processing to GPUs. So these are all examples of input data libraries. And so I'll use tf.data kind of as a running example, since this is sort of what we built on for the remaining things I'll talk about in the talk. And it's open source, and you can it's what we use at ETH as well to build on top of. So this, what tf.data provides is it provides to users an API in Python that they can use to define their input pipeline. So there's basically a library of operators that you can compose in a chain to build like a graph. And you can also parameterize these. So you can, for example, say, read this file, map, and then provide your own user-defined parse function, filter on some condition, another map function, shuffle, batch, prefetch, etc. And so the user defines their input pipeline from this chain of operators. And underneath the hood, the tf.data runtime, which is implemented in C++, it takes this input pipeline, which is represented as a graph, and it figures out how to run that graph most efficiently. And so it applies optimizations like software pipelining and parallelism. It can actually look at this graph and use kind of a TensorFlow graph rewriter to do standard optimizations like operator fusion, etc., vectorization. And then auto-tuning is sort of this idea of dynamically optimizing how many resources you give to different operators in this pipeline to try and maximize throughput. So the way this might look if you're actually kind of writing a simple tf.data pipeline as a user, you have this dataset object. You start by usually some kind of read operation. Then you apply your user-defined preprocessing here. You batch data for training efficiency. You can apply a prefetching operation to overlap data processing and loading onto the accelerator. And then you're ready to feed your data set to the model for training. Now, I mentioned that the runtime underneath the hood is implementing all kinds of optimizations. Some of these are static optimizations like graph fusion. So for example, this map and batch can be fused under the hood. And then another optimization is software pipelining and parallelism. So you can, as a user, specify how many readers you want, how many parallel threads you want for your map function. But it turns out this is actually a bit difficult for users to know exactly how to set these parameters. And so this is where it's useful to have, instead, you can actually just use this constant tf.data auto-tune. And underneath the hood, what tf.data does is the runtime models the output latency of this pipeline by modeling each operator as a queue. So we can model kind of the output latency of each operator. They're all kind of in a graph. And the runtime is doing a hill climbing algorithm to tune how many software threads is each of these operators using and how much memory. And memory is especially for this like buffer sizes, for example. And so it'll set these parameters to try and minimize output latency and essentially maximize throughput. Question?
Yes, here you assume that data is replicated on its node, or is it start with a cluster?
Yeah, so what do we assume about how, in a distributed training scenario? Yeah, so typically what happens is each node will have its a copy of the tf.data. Each training client will have a copy of the tf.data pipeline, and it'll typically read, a fraction of the data set. So it has somehow access either to some shared file system or locally. It needs to be able to access the particular elements that it'll be responsible for. So that would be like a data parallel. If you had pipeline parallel, basically each node would have to be doing some of this data processing. We also experimented, I won't go into the details of this, or if you'd like to know more, feel free to also ask questions, but we had this project called Plumber where we looked at, what is the best way to do this auto-tuning? So tf.data uses this hill climbing algorithm. Another way to think of it is you have kind of a fixed, you have a optimization under certain constraints. So you have a fixed amount of CPU cores and memory you can give out. And somehow you'd like to define the relative cost of operators. So you try to find what's the bottleneck operator in the input pipeline and give it more resources until it's no longer the bottleneck, but something else is. And intuitively, you'd like to kind of derive this cost, where cost could be in terms of CPU time or byte spread. And if operator B is twice as expensive as operator A, then it should be getting twice the resources. And so you can cast this as an integer linear programming problem, and then this is another way to sort of do the auto-tuning. In terms of what I'll highlight here is just how much does all of this matter at the end of the day. So this is an example evaluation with 5 machine learning models. 3 are from the vision domain and 2 are from the language domain. And the baseline here is a very naive input pipeline, no parallelism, just kind of a single thread doing input pipeline processing, feeding things to the GPU. And then we see that introducing software parallelism gives you significant speedups, especially for the vision models, which do more data processing. And applying static optimization, so this is things like graph fusion, gives you additional benefits. And at this point, all of these models are no longer input bound. So and I should have explained, what I'm showing here is the end-to-end training time speedup. So all we're doing here is adjusting, turning on optimizations in the input pipeline. And so at this point, all of the model training here is no longer input bound. And we see that for the language models, because they're not doing as intensive data processing, we are more quickly able to reach the point where the input pipeline is no longer the bottleneck, right? We've got sort of more minor speedups. But for these image models, it was really critical to leverage software parallelism and these optimizations to satisfy the GPU with examples at the rate it could compute at. So this is just to show that optimizations in the input pipeline really do help translate into end-to-end speedups. But so far, what we've talked about is we've kind of assumed we're given, we're doing the data processing on the training node, and we want to make best use of whatever cores and memory are there. But a related question is, okay, but how many cores and memory should really be there? How much should we provision on the CPU and memory side per hardware accelerator? And this really, in the end, depends on the model. So what we're seeing here is the CPU cores per accelerator. And this is the epoch time, so the time it takes to train on one iteration of the data set for 3 different models. And the conclusion is that, okay, they all sort of plateau at some point. That happens because at that point, you're no longer input bound. So giving more CPU cores per accelerator doesn't help. The bottleneck is what's actually happening on the accelerator. But how many CPU cores you need to provision in order to hit that point depends on the model. And so there's kind of no one size fits all. We also, so this was kind of for benchmark open source workloads and data sets. We were also curious to what extent this is true inside, for example, at Google with machine learning training jobs in practice. So this was a study we did with 73,000 machine learning training jobs at Google. And we plotted the distribution of CPU usage and memory usage on training hosts. Okay, so this is usage, not utilization. So the way you should read this graph, it's a CDF. The way you should read this graph is this 100% was the job that consumed the most CPU cycles. This was the job that consumed the least, and this is where the other jobs fit in between. And the point here is that there's a relatively long tail. And when you pick a certain configuration for what you're going to assume as the ratio between CPU, memory, and TPU or GPU cores, you're going to satisfy some slice of jobs here, but some are going to underutilize the CPU, and some are going to underutilize the GPU because they won't have enough CPU per GPU core. And so all of this is kind of the standard argument towards you want better flexibility to be able to scale resources for data processing separately from training. And this is a graph that Marco showed this morning, that even if you get this ratio right for a job today, over time it changes. So this was an interesting study from Meta where they looked at over time, how much is the volume of data that you train on increasing? And in the past 2 years, that has increased 2x for them. And what's the kind of data ingestion bandwidth that they're training on? And this has increased around 4x over the past 2 years for them. So this also changes kind of probably the ratio of compute you need for the data processing versus compute you need for the actual training. So any questions about this so far before moving on to, yeah?
Yeah, I have one question with respect to, you showed the CDF about the CPU usage.
Mm-hmm.
Why this on the I/O from, let's say, the secondary products, and not, for example, the traffic between accelerator and CPU?
So your question is, why is this on the?
Yeah, like, for example, you might have a memory-bound application where the CPU stalls, because of the traffic between the host CPU and, let's say, the GPU or the TPU. So the CPU displays. Is this
okay? Yeah.
Encompass this scenario as well, or is it only for the
right? So here, what we're so there's kind of 2 stages in the pipeline. There's the data pre-process. There's I guess there's reading data from storage to begin with. That could be one bottleneck. There's pre-processing transformations of the data, and then there's the actual loading onto the accelerator. Here we're focusing mostly on this pre-processing step, like when how much CPU and memory do you need to do these data transformations? For the storage part, you do need to make sure that you have a high bandwidth enough storage solution so that isn't a problem. And I'll talk actually later on in the I'll present a system called Cachew that brings in caching and realizes, is reading from storage the problem, and can I put my data in some faster storage to help? And then you talked about loading, which is yet another thing. Here we assume that that's basically not the bottleneck, but we actually, I don't think we have some actual measurements that I can actually show to confirm that. But I guess it's maybe I'll just say an assumption that we make. But that's a good point. That at some point that can also become a bottleneck. Yeah. Any other questions?
Most of the cost for these companies ends up being energy. So are there any? I see that you can do pipelining, but at some point there will always be like some tasks that you're underutilizing because you're making something. Are there any knobs that you can play with from that energy perspective? So that, for example, more the tasks that might finish early could last a little longer but consume less energy for them. Is there space for that? Or?
I don't know. The thing that comes to mind with the energy is actually doing things like the offloading or trying to minimize data movement, I think, and just trying to schedule things so that you're very efficiently making use of your accelerators. So here I'm talking about it from the perspective of make sure data is always ready to load, but also even when the data is ready, is the job using the full GPU, or can you pack things more efficiently on there? Is another dimension.
And here the algorithm is assumed to be kind of homogeneous.
You can assume that it's mostly homogeneous. I mean, basically, I think from the cloud provider perspective, the more different configurations you offer, the harder it gets to maintain this hardware at scale. So you try to minimize the number of configurations you have. I mean, at Google, basically, they have these huge TPU pods that then can get divided into, some smaller regions, but you don't have infinite freedom in how you partition this thing. Yeah. Okay, great. So we talked about, okay, if you're given a fixed amount of compute and memory on that node, you can figure out how you delegate it to different operators. But at some point, you may just not have the right ratio of host to accelerator resources. And so what we'd like to do is actually be able to independently scale CPU and memory for data processing from the accelerators we need for model training. And this is actually an approach that has been taken recently at least publicly, by Google and Meta, who have both published papers explaining their solution. So I'm going to talk about the Google system, which is called tf.data service, because this is what we build on at ETH also to build kind of a multi-tenant service that I'll talk about as well. But actually, a lot of these ideas, I mean, the main idea of decoupling and disaggregating data processing is very similar to Meta's DPP system that they describe in this ISCA paper. So the idea here is, before we had this training job, and whatever data processing it had to do for whatever fraction of the data it was responsible for, it was doing locally on the same machine. But now what we'd like to do instead is say, here's a service that we spin up, and we can register the input pipeline. Remember, it's represented as a graph. I can send that graph to some centralized dispatcher. And then I can spin up a bunch of workers that, conceptually, these workers, one worker or so can be still on the local client, but these workers there's nothing special here that makes it such that they need to be local to this training client. We can recruit workers from across the data center that have some spare memory and CPU cycles. And then these workers can actually execute the input pipeline, and the dispatcher tells the client, to get your data elements, contact workers at these IP addresses. And what these workers provide is the ready-to-go pre-processed data that the client can then load onto the GPU for training. And the way this actually looks, going back to our tf.data pipeline, it's actually just a minor change to your source code. to just take your data set that you constructed and call distribute on it with the particular IP address of this dispatcher or controller of the service. And so I guess the big question here is, how much does this actually help performance? And we wanted to sort of, this has been being used internally at Google. Meta also published that they're using it, but there wasn't really so far yet like a quantitative analysis that says at the end of the day, how much does this actually help performance? And even more of a question is, how much does it help overall cost? Because the whole point of doing this disaggregation is that we can scale out data processing and we can use more workers, but those workers also cost some resources. And so the main thing is that the main benefit, okay, so we do get huge benefit. I mean, here we're looking at, the study was done internally at Google with 3 vision models. So on, on that spectrum, these are models that are part of this long tail that do require a lot of CPU intensive data processing. And what you see here is the normalized end-to-end speedup for training these models. The baseline here is co-located data processing. So this would be without using the service, no disaggregation. You're just using whatever local resources you have on the training host. Versus in orange is the case where you enable scaling out data processing. And then ideal is kind of just a sanity check to see, are we able to meet are we reaching how far we could go? And the way you can test this is, create an input pipeline where you cache an element in memory that's the right size for your model and just feed that thing constantly to the model. This would not train to any reasonable accuracy, but it's just kind of a throughput test to say, how fast could I go if I had a infinitely fast input pipeline? Okay, and the point here is that with disaggregation, we can reach that speed of the input pipeline. And this, especially for some models, results in even 2 orders of magnitude speed up. So because we're removing that input bottleneck. But then the question is, we achieved that speed up by using a bunch of extra CPU workers, and some of these jobs require even hundreds of CPU workers. So how much does this really mean at the end of the day for cost? Okay, and the cost figure looks like this, where we have these 3 different models again. And we have the cost as a baseline is the cost with co-located, and the cost savings are in orange here for the disaggregated solution. And so we still achieve significant cost savings, not quite as big as the speed ups, but the reason why most of the cost savings here are coming from the fact that the job finished so much faster that we had to, we occupied, and what's most expensive in terms of resources that this job uses are the TPUs in this case, or GPUs. And so because we had to, we only had to use them for less amount of time overall, that's where the savings come from. Question left for him.
Yeah, I understand better the left. So the case of the co-located, right?
Yeah.
How is that being normalized? The ideal it's kind of clear, and you have, take pipeline. In the case of
The ideal,
the ideal is clear. But the case of co-located, you presumably are a complete bottleneck because you're actually doing the same data processing.
Yes.
Is that done, using all of the local resources available? Are you limiting the local resources?
Yeah. So in the co-located case, we basically this is whatever the Google these models run on particular TPUs. And a TPU to CPU memory ratio is kind of fixed in the data center. We sort of don't reveal the exact ratio, but you can imagine it's quite close to when you rent a TPU in the cloud, for example. There's some kind of ratio that these come in. And if you just use that ratio and use whatever local resources you have attached to the TPU, then you get some kind of training time. And you get a reduction in the training time by this factor when you enable disaggregating. And here I'm kind of magically assuming how much to scale out. And in a bit later in the talk, I'll talk about an actual policy for how do you know how many workers to actually use.
So in order to get there, it also lost property of specific models and how much.
Yes, yeah. So the ideal pipeline is not really executing the pipeline. It's just saying, imagine I had infinitely fast pipeline. Whenever you want data, it's right there. And then the limit is the model. And so we're just showing here that we've done as much as we can when it comes to optimizing the input pipeline. The rest, to optimize this job further, you need to do something about the training side. Yeah. Was there another question here? Okay. Yeah, thanks. So because the GPU and TPU hardware is so much more expensive, essentially, it's worth spending these extra, potentially significantly extra CPU resources to remove that bottleneck, and therefore even your cost savings are still significant. So that's the idea of disaggregating. I didn't spend too much time on the actual mechanism because I think it's also the idea is kind of reminiscent of disaggregating storage and memory from compute. So it's kind of the equivalent in this ML training environment. But what I want to touch on next is, can we push this further, right? Now that we've decoupled data processing from the training, can we leverage the fact that we have a global view of data processing across multiple jobs now? We actually didn't have that before because each job was responsible for doing its own data processing locally. There was no centralized component that had knowledge of what data processing is happening. And so one question we ask is, can we actually operate data processing as a service for users, take care of decisions like how many workers to scale out to, but potentially also leverage somehow a global view. So this is what I mean. We have so far talked about tf.data service, where the idea is you have a training job, you spin up a service on the side, and you launch a certain number of workers, and those workers are used for your job. But we could expand this and say this is not just for each user you have, or for each job you have your own service, but this could be a shared service that globally, adds workers, removes them as necessary, and jobs come and go. And this dispatcher now has a centralized view of this data processing. Why might you want to leverage a global view? It turns out that there's a lot of repetitive data computation that's happening in input data processing. So this is again from this Google study, where for a 1-month period, we studied millions of jobs. And here this is the CDF, where on the x-axis, we order unique input pipelines that we saw during this 1 month, from most to least frequently executed. And here in the blue line, we show what's the CDF of input pipeline executions. And then the orange is input pipeline executions weighed by their computed cost. So these big orange jumps are places where, this is an input pipeline that was particularly expensive to compute, and weighed by how often it was actually executed. And what's interesting, if we take kind of the 1/10, like the 10% fraction of input pipelines, they account for over 75% of input pipeline executions, and over 70% of the time spent doing data processing. So there's a few basically heavy hitters. There's a few input pipelines that if we could sort of avoid doing that data processing, we'd dramatically reduce the compute energy spent on data processing over all these jobs. Why is that the case? Intuitively, it's because of things like hyperparameter tuning. Often machine learning training has workflows that involve tweaking the model, but essentially you're doing the same data processing, you're reading the same data, you're applying the same transformations. And this is basically some kind of low-hanging fruit here. Now that if you have this global view, you can actually detect these things and be smarter about it, cache some results and reuse them, for example. Question?
This practice across different modalities?
Like with the models? Yes, yeah. So this was basically, we looked at around 2 million jobs at Google that use tf.data. And so tf.data is being used by vision and language, speech. Yeah. I don't think it's quite like an even weighing all of them. We didn't actually study that too carefully, but yeah, it's across modalities. Right, so what this motivated us to build a system we called Cachew. It's built on top of tf.data service, so it inherits this disaggregated architecture, but it expands it by providing this kind of multi-tenant view. And the other thing that it does is it decides, decisions that might have been hard for the user to make, like how many workers should we actually need. The other thing that Cachew does, and what the name comes from, is caching. So storage might actually be a bottleneck if you're just reading from some slow cloud storage bucket. And we'll see that we actually need a policy to determine which data sets are worth caching. They could be the source data sets, or they could be some sort of preprocessed or partially preprocessed data sets that can be stored in faster storage that is managed by this Cachew service. And then you can read your data from there. And so basically what this Cachew service addresses is these two major challenges. One being, if you recall this graph of every model is going to need some different ratio of CPU and memory resources to accelerators. With auto-tuning, we just said, given some ratio, how best to allocate it to different operators in the pipeline. But now we need a policy to actually say how many resources should we consume. And we also need a policy to tell us when it actually makes sense to cache. And maybe it sounds strange, but caching doesn't always actually help. It's not like caching will always improve what you really care about, which is the time it takes to train your model. The reason is because input data processing may not be the bottleneck, right? It's not the bottleneck for every job. So if you just blindly try to cache data sets, you may be just consuming, extra space in your fast and expensive storage without it really benefiting performance. The other thing to be aware of is that oftentimes this data processing expands the volume of data. So you started off with 50 gigabytes, but because you do some decompression, you do some casting to particular data formats, what can happen is that the final data set that you feed, the final volume of data that you feed to the accelerator can be significantly larger. And then reading that from storage can, turn into, you can have bottlenecks at the storage layer. And so you also need to find out if that's the case, or if, maybe reading the smaller data set and transforming on the fly would have resulted in a similar throughput. And then the other thing to just be aware of if you're caching data within a job is that if you're not careful about how you do this, you can actually end up affecting the accuracy of your model. So if you recall, I said oftentimes you apply some kind of random transformations to your data. And if the point was that every time you revisit that data set, you should apply a different random transformation. If you just cache what you got from one epoch and reuse it, then you remove that randomness, and that can actually hurt your model. So you do have to be careful about when you apply caching. And in the system that I'll present, Cachew, we actually kind of decide that this is a bit outside of our scope, because analyzing how accuracy is affected by reuse of data is quite complex. There are some papers that look into this. And what we just assume is that the user tells us up to which point in the pipeline they're willing to have caching introduced and so on. And this is done through a hint that I'll show you an example of. And what Cachew will do is just look at a systems perspective and say, when can caching actually give us throughput improvements and cost improvements? Okay, so these decisions are difficult for users. That's why we want to automate it, and the system is open source. And let me tell you a little bit about these two key policies. The auto caching is what I'll start with, and then I'll talk about auto scaling briefly as well. So how do we decide when something is actually beneficial to cache? I said that deciding actually what can impact accuracy and so on is a bit difficult. So what we do is we ask users to give us hints. So here's an example of a slightly more interesting input pipeline where there's some kind of data processing that is deterministic, followed by this rand augment, which introduces randomness. And what a user can provide is tell us their kind of candidate caching locations. So auto cache is an op that we add to the tf.data API. And it says that a user is saying this is from a machine learning accuracy training perspective, a valid point to reuse data in the pipeline. If this turns into an actual caching op, it means that everything before this is just memorized, like read from storage, and anything after gets computed. And so this is safe to do up until here. But then for stuff that does random augmentation, you want to actually do computations. And what the system will do is look at all these auto caching candidate locations and pick which one, if any, can be replaced by a real actual caching op and improve throughput. Otherwise, the auto cache just gets treated as a no op if it's determined that it would not help performance. And we're going to pick at most one location. Right now, we sort of ask the user to provide hints for all possible candidates. I think really in practice, just sort of the latest, safest spot should be sufficient. And then anything before that can also be considered a candidate. So how do we actually, we look at these auto-cache candidate locations, and how do we actually pick where, if at all, to insert caching? And here what we leverage is that training is an iterative process. And so there's a lot of repetition that's happening. We can learn a lot by observing the first epoch of training and then apply optimizations for the remaining epochs. And so what we look at is we collect statistics under the hood. We look at how much time does it take to go through all the operators in the pipeline. And that's the time it would take to execute if we didn't do any caching. We also look at the size produced by these auto-cache op locations in the pipeline. And we have a model of the actual storage we're using, and we say, if we were to read that volume of data from storage, how long would that take? And then we compare what is the projected read time of the result versus the compute time, and we pick whatever is fastest. And we repeat this for each auto-cache op, and we pick the one that is the lowest latency, so would give us the highest throughput. And then we compare it to what if we just didn't cache at all, and we see which one is most efficient. So that's kind of at a high level what the auto-caching policy is doing, and it's really leveraging statistics that we can collect while the job is training. The other question is, how many of these workers to allocate to a particular job? And for this, the intuition is that you want enough workers to remove the input bottleneck. That was key for performance. But any workers you add after that are just extra cost and don't really do you any good. So again, how do you estimate when you've reached this correct point of having enough workers? What you can do is monitor batch time. Okay, this is kind of a good indicator of what your epoch time will be, and something that you can observe as you go. And the batch time will be composed of time to wait for data to become available, plus time to train on that batch of data. Turns out that actually deciphering how much of the batch time was spent waiting on data versus training can get a little hairy, but one easy thing you can do is you can dynamically adjust the number of workers as you go. And if the workers are helping with data processing, so the more workers you add, the less, the faster they fill this buffer with data, and the less time is spent being blocked on data. If you keep adding workers, at some point you plateau and you realize you've hit the point where model training is the bottleneck, and so you can scale back and you found kind of your optimal number of workers. And adding these workers in and out is something that you can do while the job is training. So this is how we do it in Cachew. So just kind of giving you an example of putting all these things together. Let's say we have, so this is kind of how things go over time. I'm going to gradually reveal the graph. And what you see on the x-axis, on the y-axis, is how many workers are being used. Okay, so we start off by using a single worker. A job comes in, and here we're using the auto-scaling policy to figure out how many workers are optimal for the job. So we overshoot a little bit and realize 3 workers is sufficient. This is the first epoch of the job, and during that first epoch, we are, computing the input pipeline and also making an auto-caching decision. It's at this epoch boundary that we apply whatever our caching decision was, and here we decided. So this is a RetinaNet object detection model where we decide to apply caching at the end of the pipeline. And now in this next epoch of the job, we're going to be again computing the input pipeline, but this time also saving it to our fast storage. And we kind of restart auto scaling here. We could have also maybe just scaled from here. And then if you continue focusing on the red line for this job, we can from then on just read from the cache. So here we had to compute to even figure out, is it worth caching? Here we computed and wrote to cache, and from here on, we don't need to compute. We can just read the results from storage. And this helped us actually save 1 worker because the per worker throughput has increased. And so to actually satisfy the input demand of this job, we now need 2 workers reading from cache. And the other benefit that's happening, remember, this is a multi-tenant system. So now there's this blue job that comes in, and it happens to have, the way we've designed the experiment is that it happens to have the same input pipeline. But so it matches, so it can read from cache right away. It doesn't need to go through this process again. And notice it converges to a different number of workers. And this is because even if your input pipeline is the same, it doesn't mean that your training client's ingestion requirements are the same. So for example, this job can be using a 2 times faster GPU and therefore need more workers to satisfy its input pipeline. And so we do this auto-scaling independently for each job, but the caching, hit detection, and reading from cache can be shared across jobs. Yes, question?
Here the assumption is that you have one level hierarchy of tasks.
Yes. So right now we assume that you have. So the question is, what assumption do we make about the caching hierarchy? We basically assume you have some cloud storage, and then we have at least conceptually one layer of cache managed by Cachew. This could be composed of multiple storage media. Right now we just use like NVMe SSDs as this caching tier. But that's a potential extension where you might want to have multiple tiers. Yeah. Okay. So maybe I'll just kind of start wrapping up with a few concluding thoughts and about how we could push this sort of system perhaps even further. What I've talked about so far is really on the system side, like how can we improve the throughput and cost of training. But I think it's actually a potentially powerful paradigm to have this global view of data processing to potentially actually help you make better decisions for model quality and not just speed. And so can we, for example, see what data have other jobs trained on that might be similar to this job in some sense, and recommend relevant source data sets to other jobs. This might be a problem, if you don't have enough training data for a particular job, but you're maybe not aware, it's maybe still in your organization, but you work in a large company with a bunch of engineering teams separately collecting data sets. This could be potentially using some kind of centralized service can potentially help you discover data sets that can help your job train to a better accuracy. Also, it turns out that designing augmentations inside of these data processing pipelines is kind of a whole art or science to itself. And so there's been, for example, some work on using reinforcement learning to search the space and just design these augmentation techniques. But this tends to have high cost as well doing this search. And so maybe with a centralized data processing service, you can make recommendations of which data augmentations worked for which jobs, and maybe can translate to others. And then on the other hand, maybe you just have almost too much data to train on, or it's just too expensive to train on everything. But can your service recommend which training examples are most relevant? And so this goes towards kind of the data efficiency aspect to reducing the cost of training. And so another thing I'll kind of, that's related to this data efficiency is just kind of an anecdote of, or a disconnect I noticed between working on input data processing in an industry setting at Google, and then working, continuing to build on these systems and this research question from academia. One thing that I noticed is that the assumptions we make or the types of workloads we work with can differ quite a bit. And one big aspect that I noticed is to do with kind of the dynamic nature of data. So when we look at research data sets and the kind of benchmark we use as academics, you might use MLPerf, for example. You might train on something like ImageNet. But this is a static data set. It is, you download it at once, you have access to the whole thing. A lot of times, though, in practice, if I look at sort of what type of workloads jobs at a company like Google, or probably similar in a lot of other industry settings, data is constantly being collected, right? Whether it's a click stream, whether it's images from cars driving around, some kind of sensor data. Most commonly, when you're applying ML, it is often in settings where data is dynamic. It's either always being collected or it might need to be deleted because of privacy or other legal constraints. And so I think it's actually important that we also have some way of analyzing ML in this kind of context in a research setting. And I think there's a lot of interesting systems opportunities to build data importance aware caching strategies, training strategies, detect when you have drift and how you even need to adjust your model. And so some of the things we're doing are building an open source benchmarking suite and framework, that should say. And this is still in the very early stages, but 2 PhD students in my group, including Fatini, who's here, are working on this, and we'd be happy to chat more about that. So speaking of collaborators, I just want to conclude by thanking the amazing set of collaborators I've had a chance to work with on the work I presented today. So Dan Grauer is the PhD student at ETH who's leading the Cachew project. And we've worked closely with Google. There's also some collaborators from CMU on the auto-tuning work. So just wrapping up, we said ML has a huge cost and resource efficiency problem, often caused by the input pipeline if we're not careful about how we design that system infrastructure. And one way to really alleviate that pipeline, that input bottleneck, is to allow us to scale out and disaggregate data processing from training. And so we built a system called Cachew that builds on tf.data service and gives you this multi-tenant view that we hope can be a useful research platform for ongoing work. So thank you very much, and happy to take more questions.